So today I want to begin with what we have done yesterday, right? So I want to go back to patch models, right? And now I want to explore in a bit more detail and explore a bit more how we model populations in space, okay? Populations in space. So this is, so I'll go through. So we are going to pick up where we stopped yesterday, work on that patch model exercise, and then I'm going to use it to explore a few scenarios and explore a bit more what happens with that, okay? And with that, we are going to go a bit into perhaps one of the main tools of terrestrial exploration in spatial ecology, right? Spatial ecology is kind of a funny name, right? So it's, when you say that you study spatial ecology, your friends and family look at you kind of funny, right? Spatial ecology, right? So it's not what it looks like, right? So yeah, so populations in space, okay? So this is yeah. So let's do that, and then we are going to talk a bit about diffusion, okay? So yeah, so this is the idea today. Let's go. Okay, so no, what's the issue here? Okay, so here it is, populations in space. Let's go. So the first thing here is, okay, let's go back to yesterday, to our patch models, okay? I think we have we already had gone into a bit of detail about this model, right? So I have that each patch I has a logistic growth, and then it sends immigrants out to other patches, right? So with a rate of MJI, okay? So MJI means individuals leaving patch I, arriving at patch J, right? And then it receives individuals from all the other patches J. So you see here MIJ are individuals that leave patch J and arrive at patch I. That is the one I'm looking at. And then yesterday we saw how we can express this in matrix notation, okay? In matrix notation, it looks like this, okay? Okay, so we had this as an exercise yesterday. I think many of you were able to do it, yeah? Yesterday, but now this is the solution now, right? So it's you have essentially three parameters here, the array of R's and K's, and the matrix M of migration rates, okay? And then you just receive R, K, and M besides Z and T, and now you have R times S times 1 minus X over K. Over here, that is the first term, and then you have this here is the sum over the columns, right? So we have discussed this, right? So along the columns, right? So I want to sum all of the lines of this matrix, okay? So this is, you see here, for each column I, the second index is the column, I want to sum over all of the lines, right? So I have to sum along axis 0, okay? So this is what I do here. And I take this will be an array with one value for each column, right? And I multiply this element by element by the array X, okay? And finally, the last term here is just the matrix product of M by N, okay? By X here in the notation here. Okay, this is okay. Are there any questions? Yeah? Good? Okay, good. So now let's explore this a bit, right? So I think yesterday we didn't have time to explore so much. So let us explore it a bit, right? So let's start with only 5 patches, right? So only 5 patches. I'll put the growth rate equals to 1 for all patches, and the carrying capacity also equal for every single patch. So it's all equal to 10, right? So this is an array of 5 ones multiplied by 10 is all 10s, okay? And now I want to write down the migration terms here, okay? So I construct an array made by ones also, but this is 5 by 5, okay? 5 by 5. So this is a 5 by 5 matrix, and I multiply it by 0.05. I mean, this is the migration rate from each patch to any other patch is going to be 0.05, okay? And then I have this function fill diagonal that takes this matrix and put zeros in the main diagonal, okay? So before I won't go further, let's run this and let me print this stuff here, just so we are sure that we're not doing anything wrong, right? So here is R, so it's all ones. Here's K, the carrying capacities, they are all 10. And here is my migration matrix that is all 0.05, except for the main diagonal that is all zeros, okay? Yeah, so far so good, yeah? Okay, and now how we solve this model, we just call ODEINT again. I have to have an initial condition, and now for the initial condition, I don't want to put all of them equal to something, right? Because otherwise, all of the patches, for instance, if I do this, right? So if I just do once, I don't know, n, right? So if I do this, the plot is going to be very boring because all of them, all of them start at 1 and go up to 10, right? So this is kind of boring because you don't see anything, right? So here what I did is I started each one with each patch with a different condition, different initial condition. So starting with 5 and then with 7, 9, 11, 13, 15, right? So then running this here, it means patch 1 starts here, maybe even put a legend here, right? So 1 to 6. Okay. So patch 1 starts here with only 5 individuals, patch 2 starts with 7, actually 7 and something, right? And patch 3 starts with 10, patch 4 starts with a bit over 12, and patch 5 starts with 15 individuals, or 15, not individuals, but some unit of population, right? And they all converge to 10, right? Because their carrying capacity, the carrying capacity of all of them is 10, okay? Yeah, so this is more or less what we expected to happen, yeah? Or not? Yeah, they converge, all of them converge to 10 eventually, okay? But then, all of their carrying capacities are 10, right? Yeah, so this is kind of boring, right? So what's the role of migration here? Yeah, so the thing is, well, what if instead of having migration here, if migration were 0, yeah? There's no migration at all. Does it change anything? So now I don't have migration at all, right? So does it change anything? Not much, right? Not much. So really, migration here is enough pointless, right? Because they are all equal patches, they are all growing to the same carrying capacity, and so on, right? But maybe if we had a very large migration, so let me put, I don't know, maybe 5 here, right? So a very high. You see that this is a rate, right? So I have to compare this to the carrying capacity, to the growth rate. Okay? That there's also units of time, okay? So this is very much larger, 5 times larger than the growth rate, right? So this now should be a little bit different. You see that now they converge to 10 much more quickly, right? Because now the time it takes to reach 10 is done not only by growing locally, but also by exchanging individuals among the patches, okay? So they all go to 10 much more quickly because they are exchanging individuals between them much faster, okay? But this tells us something already, right? So this tells us that in order to understand what goes on with migration, the growth rate is kind of, it's evening things out, right? Because all the carrying capacities are the same, so it's hard to understand what migration does together with the growth rates, okay? Yeah? Does that make sense? So we are going to go in a different direction here. But before that, maybe we do something else here, right? So let me go back to no migration, okay? No migration. And instead of having all of them equal to 10, right? So all the carrying capacities the same, let's maybe try to do this. So a link space creates an array from, I don't know, maybe 2 to 20. With n elements, okay? So we have used linked space before, right, or not? Yeah? Yes. Okay. So this is then, so then the carrying capacities are not equal, right? So there are 2, 6.5, 11, 15 and a half. Maybe I would use something more, maybe from 5 to 20? No, 4 to 20. So they have round numbers. Oh, nice round numbers. Yeah, 4, 8, 12, 16, 20. Okay. And now when I run this without any migration, what is going to happen is that each of them is going to go for 4, 8, 10, 12, 14, 20. Sorry, 16, 20. Okay, you see that? Yeah. So they're all going to go to their carrying capacities, and there's no migration at all, right? But then if I include migration, if I include a very small migration over here, right, doesn't change much, right? So let's see. You see that they are still going to almost the same, but you see that now the top one is not going to 20, it's going to be below 20. And the lowest one that was 4 is now closer to 5 here, right? So let me print the final element here, right? So yeah, something like this, right? So they're not going to their carrying capacities anymore, you see? The ones below the average here is 12, right? So the ones below average are a bit above their carrying capacities, right? So the carrying capacities were 4 and 8. They're at 5.2, 8.7. And then the ones above, they are below their carrying capacities, right? Because they are sending out more individuals than they receive, right? So this is a kind of what we call source sink, right? So places with large populations send out more individuals than they receive, okay? And of course, this effect is going to be stronger if I put a very high, so let me put maybe 1 here, okay? A higher migration rate, okay? If I do this again, now I have the populations are much closer together, you see? So even the lowest, the patch with the lowest carrying capacity goes to 8, and all of the others are close to 9 and 10, you see? Even the one with 20, right? The 51 here was 20, its carrying capacity. Now, the final population here is only a little bit below 11, right? So you see that migration has this property of homogenizing the system, you see? Okay? There's also this thing that we consider that all patches are equally connected, okay? So, of course, when you have a geographic distribution, right? So, as the map, I don't need to redraw the map, right? So, if I have a map, right, with patches, of course, they're not all equally spaced in the sense that there are some patches that are closer together and you expect them to exchange more individuals between them than if they are very far apart, right? Yeah? That's reasonable, right? Yeah? Yes or no? Yeah? So, of course, depends a bit on the scale, right? So, of course, if I have a very mobile species and I look at a very small region, right? Of course, it can go everywhere, right? So, if I take just a small part and I have a bird that can fly around in a single day, the whole park, of course, it doesn't really matter, right? Then it's all equally connected. But for larger range migrations, right? So when this distance is such that it takes a long time for the individuals to cross this landscape, then of course you expect patches farther apart to be less connected, so I have a lower migration rate between them than patches that are close together, right? Yeah, so far so good, yeah? So, okay, so let's go back now to the idea that, okay, here we have growth rates interacting with migration, okay? So, but a different way to look at this to understand migration is to turn off, at least temporarily, turn off the growth rate, okay? Let's look just at migration with no growth rates at all, right? What does that mean? So if I put r equals to 0, okay? If I put r equals to 0, it means that there's no growth at all, okay? So this first term here of the equations is always 0, and you only have populations moving among the patches, right? So the first thing that we can understand about this is that if that's the case, then the total population is going to remain constant. So if I have an initial condition with, I don't know, the total number of individuals, they are only going to move around. They're not going to die. They're not going to to reproduce. So they are going to keep at a stable value, at a constant value, but their distribution among the patches is going to change due to migration. Yeah? Okay, so let's try to do this. Okay, so let's come here, and now 5 patches again. Now I put R equals to 0, you see here. So this is all zeros. Okay, let me do as I did before, right? So to print this stuff here, I think it's useful, right? To be sure that we are not doing something weird here, right? So now I have the R is equal to 0, all the N capacities are 10, but it doesn't matter anymore, right? The N capacities, because there's no growth at all, okay? And now I have, once again, all of the migration rates equal to 0.05, okay? And here I, once again, now I put a very lopsided initial condition here, right? So I have some patch with no individuals at the beginning, one with only a little bit, and then another one with 50 individuals or 50 population, right? So not sure if this is individuals actually, right? So what should happen after some time? What do you expect it to happen, right? So the total population is going to remain constant, right? So if I have the total population here is 50, 70, 80, 81 population, okay? Yeah, so the total population across all the patches will be the same, right? Then migration is symmetric, right? So they're going to move around, right? Eventually, what do you expect to happen? Places with more individuals will have more individuals leaving than arriving, and they should eventually be evenly distributed, yeah? Yeah, so I should expect to have 81 by 5, it's about 16 individuals, 16.2 individuals per patch, yeah? So let's try that, right? So let me also print the last value here, right? So yeah, looks like my prediction was kind of okay, yeah? So you see what is going on here, okay? So I have here the 5 patches. Maybe I could also put the legend also here, yeah? Yeah. So you see here, so the one that started with 50 goes down, the one started with no individuals goes up, and then they all go to an equilibrium where they are evenly distributed, right? Why did that happen? Because migration is symmetric, okay? They are all patches, send individuals to all of the other patches and receive from all the other patches with the same migration rates, yeah? Okay? Of course, I can make this go slower or faster depending on the migration rate, right? So if I put a very large migration rate here, so I put this equal to 1, the same stuff happens much more quickly, you see? Much more quickly, right? And if I put a very small value for m here, for instance, if I put 0 here, it means that nothing happens at all, right? So, so the populations remain exactly at their initial condition, yeah? And if I put a very small m here, maybe 0.001. So they are changing, but they're changing very, very slowly. Like maybe 0.001 was too small, right? So maybe this one here. Right? Yeah, you see they are converging to the same values as before, but at a much slower pace, okay? So migration rate tells me the scale of time in which I have this evening of the population, this homogeneous distribution of the population, okay? Yeah, so I can measure this by the time it takes for this stuff for all of the population to be the same across all the patches. Yeah? Question? Yeah.
A question about the formula, since we actually saw the equation yesterday. If I remember well, this equation of the patches considered some sort of competition or mutualism between the species, or did it not?
This here?
Yes.
Okay, so this is logistic growth inside the patch, okay? Yes. So this means that in each patch, I have a population that grows and there's some interspecific competition. Mm-hmm. Yeah, that's all, but only among the individuals in that patch, right? Not across all the region, right? So Yeah.
Also, we are just dealing with populations of, I don't know, species or not.
Yeah, there's only a single species here, and there's subpopulations, right? So there's a population of that species on that patch, in the other patch, in the other patch, but it's all the same population. The individuals that leave this patch and go to the other patch are incorporated in the population of the other patch.
Okay, mixed things. I thought we were
because there was
talking.
another example with competition and the generalized loss of Volterra, right? So maybe.
Yeah, I was thinking about interspecific competition. Completely
this
different.
one, right?
Sorry.
So this was the example, but this here, the numbers here means different species, right? Different species. In this other example of our patch models, the different numbers mean different points in space, okay? So all the populations are the same species, but they are exchanging individuals between patches, okay?
Okay, thank you.
More questions? Okay, so now what do I want to do, right? So now, well, I want to try to make a more realistic model in terms of capturing this characteristic of close neighbors exchanging individuals with a higher probability or with a higher frequency. Okay, so I'm going to go already to the extreme case. Okay? The extreme case is I'll put. I have a drawing here that is pretty bad, right? So maybe let's do this on the board. So the situation I want to do is something like this. I have a patch here, right? I have a patch here, and then I have a patch here, and then I have a patch here, and another one here, and another one here. And I'm going to say that there are 5 patches over here, and then populations only migrate between nearest neighbors, okay? So I don't have migration as before with all migrating to all of the others, okay? I only have 1 going to 2 and 2 going to 1, 2 exchanging individuals with 1 and 3, 3 with 2 and 4 with 3 and 5 only with 4, okay? So I only have the closest neighbors, and I'm assuming that they're along the line, okay? Yeah, so it's kind of one dimension here, okay? Yeah, so I want you to write down, so this is the next exercise. Yeah, I want you to write down a matrix that that represents this this situation. Okay, so so what should the matrix M, the migration matrix, look like? Okay, so we can write this. You can think, for instance, for I don't know, maybe take only 3 patches and write it out by hand. Okay, but then think about what would happen with 5 patches or 10 patches. What does this matrix look like? Okay. Yeah. So this is. I'll give you a few minutes to work on that, and then we go back to try to implement this. There are several different ways of implementing this, but first let's think about what this migration matrix should look like in this case. Okay. Yeah. Let's try to do that. Okay. Again. So let's solve this, right? So the idea here is that we want to write down our migration matrix, right? And the simplest way to do this is, okay, this is 5 patches, okay, 5 patches. So I can just write down my matrix M, right? And you remember that each element in this matrix here, so I have 5 lines and 5 columns, okay? Each element here, so this is M11. This is migration from patch 1 to patch 1 that is 0, okay? I don't have, I think I'm ready to tell you that all the diagonal elements, the 5 diagonal elements will be 0, okay? They will be 0 because there's no migration between the patch and itself, okay? Okay, now I want migration between patch 1 and patch 2, right? So this will be this element here. Would be the M12, right? What is M12? Is migration from patch 2 to patch 1, right? And you see they are connected, right? So this is going to be some value, okay? I told you that they all have to be the same value, so I put just M here, okay? I see that There is some value m here, okay? And the same for going from patch 1 to patch 2, right? So m to 1 over here is migration from 1 going to 2, okay? So this is also going to be m, okay? Yeah? Okay, so this line here, so this is migration from patch 1 to patch 1. This is migration from patch 2 to patch 1. The first element here is M13. That is migration from patch 3 to patch 1. But patch 3 is not connected to patch 1 now, okay? So what is the value of this guy here? This is 0, right? This is 0. So this is 0, okay? This is 0. And the other elements in the line here also will be 0, right? So the other element here is migration from 4 to 1, and the last one from 5 to 1, right? So this is 0, and this is also 0. Yeah? Okay, good. Now for patch 2, right? So patch 2 is receiving individuals from patch 1 and also from patch 3, right? So M23 here, that is the migration from 3 to 2 is going to be M. But then from 4 to 2 and 5 to 2, it's 0. Okay, so this is 0, and this is also 0. Yeah, questions? Is it clear to everyone? Yeah? Yes or no? Okay, good. Okay, now it's becoming kind of simple, right? So now I'm going to go for the third patch, patch 3 here. Let's number this, right? So, yeah. Right, so from patch 3, patch 3 receives individuals from patches 2 and 4, right? So the second column will be M, the fourth column will be M, the first and fifth columns will be 0, okay? Yeah, like this. Yes? Fourth patch, right? Fourth patch receives individuals from patches 3 and 5 and not from patches 1 and 2. So from patch 1, I receive 0, from patch 2, 0, then from patch 3 and 5, I receive M, right? And finally, patch 5 only receives individuals from patch 4, right? All the other 3, 1, 2, 3, are going to be 0, okay? 0, 0, and 0, okay? And this is our matrix right here, okay? Yeah? Nice? Clear? Questions? Comments? Yeah? Okay, good. And then now, what is funny about this matrix, right? So what is funny is that, okay, I have my main diagonal here, the main diagonal where I equals to j, right? So migration from to itself, from each patch to itself, is always 0. And now only those two diagonals here, right? So let me put it in yellow, right? Only these two diagonals here, just above and below the main diagonal, are non-zero, okay? All the rest is 0 as well, okay? So you see that even if I had, I don't know, 100 patches, right, the structure would be exactly the same, right? If I have, instead of 5, I put 100 in a row with only the closest neighbors connected, okay? I would always have that only these two diagonals would be non-zero, okay? Would have some value, right? Because looking at a certain patch, the element in the main diagonal is 0. The first one after is it receiving individuals from the neighbor at the right, and this here is receiving individuals from the left, and all the others are 0. Yeah? It's simple to think like that, yeah? Okay, good. So now our problem is, how do I implement this in a smart way, right? Because of course I don't want to write a matrix of zeros and keep completing, saying, okay, 2, 1 is M, 3, 2, 4, 3, and so on, and eat one by one, right? I want to do this in a way that I can just say, okay, this whole diagonal is M, this other whole diagonal is also M, okay? Yeah, so how do we do that? Okay, let's see. So let me go back to the computer over here. So now there are some functions that make this that helps us, right? So we have seen field diagonal before, okay? But field diagonal is not, it doesn't do, it only fills the main diagonal, okay? Only fills the main diagonal. And we don't want to fill just the main diagonal. We want to fill these two diagonals that are the off diagonals, okay? Off diagonals, right? So fill diagonal by itself is not going to be enough, okay? So there's another function called diag, okay? Only diag or jag, right? And how does it work, right? So let me show you a few examples here. So yeah, so when you call diag with an array, right? It builds, the default thing is to build a diagonal matrix, okay? What is a diagonal matrix? A matrix that only has the main diagonal filled in, okay? So you see, I put an array of 5 ones here, okay? You know what this is, right? So it's an array with 5 ones, okay? And what does this do? It creates a two-dimensional array here where I only have, let me print some, just to, I think it's easier to see if we have more space between, yeah. Better, right? Yeah. So you see, I have only the main diagonal filled in and the rest is 0, okay? Okay, but now it also has the option of having this k here. What is this a? Is the offset of the diagonal. So if I want to fill in diagonals, off diagonals above the main diagonal, I just put this equal to some number, okay? So k equals 1 means that I'm going to fill not the main diagonal. I will create a new matrix filling one diagonal, but not the main diagonal, but the diagonal above the main diagonal, right? Yeah? So this is the diagonal here, you see? So this one here, yeah? So this is what this function does, okay? So if I put this equal to 2 here, it's going to take the second diagonal above the main diagonal, you see? So this is the main diagonal, this is diagonal with k equals to 1, this is the diagonal with k equals to 2, you see? And there's something that you have to be careful here is that we want a matrix that is 5 by 5, right? Yeah? So the main diagonal has how many elements? Has 5 elements, okay? But the off diagonal doesn't have 5 elements, it has only 4 elements. And the second off diagonal here has only 3 elements and the other only 2 and so on, right? So if you want to have a matrix that is 5 by 5 and we supply a number of ones here, this has to be, if I'm using the k equals to 1, I need only 4 elements, okay? Not 5, you see? Because it's going to build a matrix that has, where the off diagonal here has these 4 elements, right? So if I want a 5 by 5 matrix with the second off diagonal field, right, I need to, with k equals to 2 here, right? If I use 4 values, it builds a matrix that is actually 6 by 6, okay? Yeah, so we want to actually do this to have a 5 by 5 matrix. I need to do this, yeah? With only 3 values, okay? And then this is the same for diagonals below the main diagonal. The difference now is that the k now is counted in the negative, okay? So the diagonal just below the main diagonal has k equals to -1, okay? And then this is exactly what shows here, okay? Yeah, questions? Is it clear how diag works? Yeah, so we want to build this matrix here, right? So what do I have to do? I have to take a matrix that has this diagonal and sum it with a matrix that has this diagonal, right? And the sum is going to be a matrix with those 2 diagonals, yeah? So I just take them, so I'm going to, let's go here, yeah, before I go here, so my matrix M is going to be this diag here, sorry, without the print, right? So, I'm going to take this one here, plus the same stuff, but with k equals to minus 1. K equals to minus 1. Okay, let me print m here. You see? So I sum the first one that has this diagonal here, the second one has this diagonal here to get my matrix, okay? And of course, if I want to have a value of m instead of 1, right, I can just come here and say, okay, m is, I don't know, 0.05 times m, okay? And then all of the values will be 0.05. Good? Yeah? Questions? Comments? Okay. Question? Yeah.
What if we want to change the matrix size and like use n instead of 4 inside NP diag NP1s?
Because I want you to think in terms of what if I had more than 5 patches, right? If I want to have, I don't know, 100 patches instead of just 5. Is that the question?
I'm asking actually more about the code itself, like how to, if you change NP1s there to, I don't know, 10.
If I use it 5 here, for instance, then
Yeah.
this would create a 6 by 6 matrix, yeah? You see?
Okay.
Yeah. Of course, I have to use the same values here, otherwise this matrix would have a different shape than the other one, and this would give you an error, right? Of course. Yeah, so, yeah, they should have the same shape, yeah? Okay? So what should be this number here? Is actually the number of patches minus 1, actually, yeah? Because I have to have an n by n matrix, and then this should be n minus 1, okay? So this is a more general way to write this, yeah? For any number of patches, okay? More questions? Okay, so I suggested here 2 different ways, okay? Besides using this function, I could also use fill diagonal, but then I have to do some trick, cutting off some column or some line to get the same effect. Right? And then there's another different way without using matrices, okay? But then maybe we'll go back to this later, but this is a bit more, I think this is actually the most efficient way to do this, but we don't need it right now, so maybe, I don't know, maybe tomorrow or maybe later today, I don't know. If we have time, I'll go back to this, okay? But there are a few different ways of doing the same calculation, okay? Okay, so let's continue with this, right? So I just I'll put this inside this here. Okay, so maybe since I'm using m here, I'll put n at the top. Okay. Oops, over here, yeah. So I define the number of patches. I build my diagonal matrix. My bidiagonal matrix like this, and now I want to solve the model. Okay, so I put once again I use r equals to 0. Okay, so we are going to see the solution without any growth, right? So only migration. Okay, I don't need this anymore, right? Because I already filled my matrix correctly, and here what I use it here is, okay, I will have 5 patches. With the first one starts with 20 individuals, and all of the other 4 begins with no individuals, okay? And then what happens for a large time? What do you think? So now we don't have all patches connected to all the other patches. I only have the nearest neighbors connected, yeah? So what does that lead to, right? So does that make a difference? So let's see, right? So let's see. So I'm going to solve this model, and let me put a larger rate here. Oops. Oh no, let's use 1 here. Sorry. Maybe I need a larger time. Yeah. So. So you see, with m equals to 1, right? So in more or less, after some time, a little bit over 10, all of them reach the same value, okay? The same population, right? So let's print the final population here, okay? The final population here is just going to be around 4. For a long time, it's going to be exactly 4 for each of the patches, yeah? So these 20 individuals from the beginning, remember, without growth, only migration, there's no individual, there's no population going to die or to reproduce. So the total number of individuals remains exactly the same, but they're now going to be equally distributed among the 5 patches. Yeah? So is this a bit of a surprise or not so much? They are all migrating, even if they're migrating only to the closest neighbors, eventually this is evenly spread. But there's a difference from before, right? So from before, what we had is something like this. Let me go back here. I think this was the example, right? But let me put a larger m again here. So let's go back to, I don't know, 0.5 or something like that. 0.5 was a bit too large, maybe 20 times steps. Okay, so you see that I started, and let's do something better here, right? So let me use the same initial condition that I used over there, right? So with only one patch, with 20, all the others with 0, right? Yeah? So the same initial condition as we used below, okay? But this was the case with all of them connected between themselves, okay? Yeah? And here I even have not the same, but yeah, now with the same migration rate, yeah? So what happens here is that all of them go to 4 pretty quickly, and you see that there's the patch 1 that starts with 20, and all the other 4 patches go in exactly the same trajectory, okay? They all go to 4 together, right? So they are all receiving population at exactly the same rate at the same time, okay? Yeah, because they are all equally connected to the patch 1 that has 20 individuals, right? Yeah, but down here now, we have, where was I? Yeah, down here. Down here now, we see that I have the patch 1 that is going down here. You see that first, with the same migration rate, this zero is lower, okay? This zero is lower. But also, you see that patch 2, that is the closest to patch 1, goes up very quickly. And then patch 3 goes up, and then patch 4, and only at last patch 5. So you see, there's only population here. It's going to patch 2, and then it starts to go to patch 3, and then to 4, and then to 5. So you see that there's an order to this distribution here. Yeah, there's a spreading out from patch 1 to the rest. Yeah, does that make sense? So this is the difference between migration only between nearest neighbors and migration homogeneous across the whole landscape. Yeah, so you see that you have this order of dispersal. Yeah. Okay. Okay. Good. Now, there's another way to plot this. I'm not so sure this is very helpful, but I included here anyway, right? Because now, when I just number the populations, right? This plot here doesn't show me so clearly that this is space, right? That patch 1, then 2, then 3, then 4, then 5, okay? If I plot this using a heat map, this becomes a bit clearer, but this plot is terrible, actually. Yeah, so, yeah, well, this is a terrible plot, right? So, you cannot see anything, right? So maybe, the idea here is that for each point here in the x-axis, so this is 1, 2, 3, 4, 5, in the y-axis I have time, and I would see if I were seeing anything, but I don't see anything at all, actually, right? So maybe if I do a plot in a log scale, perhaps I'm having more success, right? So, and I will put vmin. So this is just a treat here to see if I, oops. So just to see, oh no, it's still bad, yeah. Sorry. Yeah, maybe I should. Yeah, it's starting to look a little bit better, but not by much, right? So, yeah. Well, I'm never going to to get this is A right? So, yeah. So the idea here is that I will see a large value here, and then it spreads out to the others, but it's not really looking very good. But just say, it starts with a lot of individuals in the first batch, and no individuals in the others, and then this decreases, and the others increase with time. But then, yeah, I think I have better plots further on. Okay, so maybe. We see better examples of these plots, right? So this is kind of hard to get the Euler scales easy to see, okay? So let's move on, and then maybe we'll see a better example later, okay? So, okay, so far so good, people. Questions, comments? So we just saw how we can model dispersal among patches in a linear direction where you only have migration between closest neighbors, okay? Now we are going to do something funny here, okay? Something funny. We want to understand what happens, because up until now we were thinking in terms of a landscape where I have patches of habitat inside a region of non-habitat, okay? Yeah, but now I'm going to change the focus a bit in a funny direction. Now I'm going to consider what if I have instead of having a region with patches, what if I have that everywhere is a patch, and I want to see how the population moves in an homogeneous region. I don't only have a landscape with habitat and non-habitat. I only have habitats, okay, but I have habitat in a line, not in a two-dimensional region, okay, only in a line. And then how do I, right? So let me try to explain this in the board. Yeah. So I have a line here, right? And the whole line here, right? The whole line here, it's all habitats, okay? So I want to simulate what happens when I have my population in the continuous space, okay? But we don't know how to do continuous space yet, okay? So instead of trying to do something continuous, I just say, okay, instead of looking at all points, I'm just going to divide this into many pieces here, and I will treat each of them as if it were a patch, okay? And I'm going to say, okay, the individuals, any individual that wants to go from here to here, right, it has to go over this point, and then this, and so on, right? So I will only have migration between nearest neighbors, okay? So I'll have this and this, this and this, and so on, okay? Yeah? So, yeah? Okay, so this is kind of funny, right? But then this is an idea of how we would try to understand populations moving over homogeneous space now, okay? I would just treat homogeneous space as, instead of being continuous, as a lot of patches very close together. Yeah? Does that make sense? Or is that too kind of arbitrary? Yeah? So I'm going to think of continuous space as a lot of patches very close together. Okay? Yeah? Okay. So let's try to simulate this. Okay? Let's try to simulate this. So the idea is pretty much the same as we just did. Okay? So now, instead of, so let me copy this M here, M that I had over here, okay, so this stuff down here, okay? So, yeah. Okay, this is exactly as we had before, I think. So with 5 patches, right? So, and you see that after this time 10 more or less, they all go to, everyone has the same population around 2, okay? But now I want to increase the number of patches, okay? So instead of 5, I'm going to put, I don't know, 50 or maybe 100, okay? Yeah? What happens if I put 50 here, okay? Now my matrix here, do you want to see this matrix or not so much? Yeah, let's look at what this looks like. Yeah, so print M here. So now this is a 50 by 50 matrix. It doesn't even show all of the matrices, okay? So yeah, so it's a 50 by 50 matrix, okay? Yeah, so let me put this together again, right? So okay, so n equals to 50, and now when I solve this, what's going to happen? So let me just see, n is 50, r now is only zeros. Remember, I'm not including growth, I'm only including migration, okay? I don't need this also. I'm going for the same time with, and now what I'm doing here is I'm saying the initial condition is all zeros, except for the first value, the first patch that is going to have a population of, let me put, it was 20 in the other example, right? So let me put exactly the same, right? So it was 20, yeah, 20, okay. Right? So only the first one is 20, okay? And then I solve this model, and then I plot it, okay? I plot it. And what happens is that it looks like they are all stabilizing also, right? They are all going to have eventually the same population, right? But it's now taking a much longer time. Right? Does that make sense? Why is that, right? Because there's something funny happening here, right? Because what we are doing now is a little bit different from the patches. Because what I want to imagine now is that I have a certain region, I don't know, from 0 to some size L here, okay? And before I divided this thing here in 5 patches, so this is the first, this is the 50, and I have the 2, 3, and 4 here, okay? And I had a migration rate between each patch over here, yeah? Okay. Now I'm going to say I want a better representation of this as a continuum here, continuum habitat. So I put a lot of patches here. So I put many patches here, many patches here, many patches here. You see? So I have 50 patches in total, right? I didn't count, right? I just some, yeah. Okay. So, but what happens now, right? So I have to go from the beginning until the other side of the line, right? Of this segment here. I have to go through each one of them, okay? One by one. I have to migrate from 0 to 1. Now this is now 20, 40, 40, and 50, okay? Yeah? So I have to go from 1 to 2 to 3, passing through, passing through 50 patches instead of just 5, okay? So if my migration rate is exactly the same as I had before with only 5 patches, this means that I take a much longer time to reach the other end. Yeah? Right? But then this is not really a good representation of the same processes just changing the divisions, you see? Because if I have that each patch is now actually points that are closer together, what do I expect my migration rate to be? I expect it to be much higher, right? Because if I went from this point to this point in a certain time, now I have to go with in several different steps here. These steps here should happen faster, right? So that the time it takes to get here is still more or less the same. Does that make sense? Yeah, so if I want to represent migration in a continuous line, right? But dividing into smaller patches, in smaller pieces, I have that as my my pieces, my number of patches become larger, right? And then my step size here becomes small, and then the migration rate that includes here should be higher, okay? Yeah? Okay, so make sense, people, yeah? Make sense or not? Good. So let's try to do this, okay? So I want to have something that looks similar in terms of the time it takes to reach a situation where all of them have more or less the same population, okay? Of course, now since we are dividing into 50 patches instead of 5, they're not going to stabilize at 4 population per patch. It's going to be at 0.4, right? Because then it's divided among more patches, okay? Yes, Sebastian. Mike? Where's the microphone? Yeah. Oh, there's another there. Do you want to?
It's working. I don't understand why the migration rate has to necessarily be faster. I mean, couldn't it just be that the species takes longer to migrate?
Well, it could, but you mean, if you're saying this, then you're modeling a different situation, right? So what I'm telling you here is that I want to model the situation where this distance is exactly the same, okay? But I'm just choosing to represent it with more or less subdivisions inside the same distance, okay? So the population has to go from 0 to L, or it has to spread out evenly in more or less the same time, no matter how I choose to divide, because this division here in 5 or 50 pieces is arbitrary. I chose this number, okay? It's not something special. It's not that. I'm telling you that this space here is homogeneous. There are no patches anymore, right? Yeah? And this size here is fixed. All I'm going to change here is in how many regions I subdivided to study this, not, you see? So to represent the same situation where the population always takes the same time to spread over this whole range, okay? I have to increase the migration rate, yeah? It's clear now? Yeah? Okay, good. So, so let's try to do this here. Okay, so I want to have a plot where this thing here, you see, it is used to stabilizing all of the populations, more or less to the same value after some 10 to 12 in time here, okay? Yeah, so I just need to increase m, okay? The migration rate here, so I multiplied the number of patches by 10, right? So maybe if I multiply the migration rate by 10, does that seem reasonable? Yeah? So let's try that. Okay. Well, still didn't work, right? So you see it's still not at the same value, right? So it's not enough to multiply by 10, right? So maybe if we multiply by, I don't know, 20? Or what do you guess here? 100. Not enough, right? Oh, 100. 100 is an inspired guess, I hope. Yeah? And you see, now they're all converging together, yeah? After a bit about, more or less 10 time steps here, yeah? So 100 is more or less what you would expect, yeah? Okay, so this is not an exact thing, okay, but it's more or less 100, okay? Okay, so, good. So this is, I think this plot was working better, okay? So this is the plot. You see, but I had to use this one, yeah, so you see, I start with a lot of population in this end here and 0 over here, right? And you see that this gets darker, has a lower density, a lower population, and all of this is going to get lighter, that is this increases in population over here until at the end they are more or less homogeneous, okay? So if I print, yeah, this is something that I should have done also. If I print here the last values, okay? The last values here, you see that they're all very close to 0.4, okay? Yeah, that means if I have 50 patches, initial population is 20, 20 by 50 is 0.4 per patch, right? So the population at the end is evenly spread, okay? Good, so now is the trick, okay? So now we actually want to go to the continuum, okay? We actually want to go to the continuum. What happens if instead of just toying around with this stuff with many patches and so on, what if we actually want to treat the space, right, the location along this axis here as a continuous value, okay? I want to have that my population m is going to be a function of x, right? Yeah, so instead of having a population at this patch, a population at this patch, a population at this patch, and so on, I'll have a density of population over the whole line, okay? So, for that, let me go back to the board, right? I think in the board it's clear, right? So, so let's try to do this, right? So, so what is the equation that we had for each of those patches, okay? So we had an equation that looks like this. So if I'm going to look at some patch over here, right? So I'm going to call this patch I, right? And this patch I, it only sends individuals to the two nearest neighbors, right? And receives individuals from the two nearest neighbors, yeah? So if I look at the equation for patch I, right, I think I had this somewhere, right? So I'm going to ignore for now the growth rate, okay? Ignore the growth rate. I'm just looking at migration, okay? Migration, right? So I'll have that I exchange individuals with patch I minus 1 and patch I plus 1, right? So I send individuals, I have a migration rate. I send individuals to the patch to the left and receive individuals from that patch, okay? I minus 1, okay? So this is the exchange I have with the patch to the left, and then with the patch to the right is the same thing. I'm sending individuals to that patch, and I'm receiving individuals from that patch as well, right? So this is the equation for this patch I over here, okay? Now this is the part where it's going to be tricky, okay? So this is population at patch I, okay? So I'm going to say that the patch I, what is the position in space of the patch I, okay? So if I have this is the x-axis, okay? So let me erase this stuff here, right? So I'm going to say that this starts at 0, okay? So this is 0, and this is an x-axis, right? And the position of the patch I here is at a position called xi. xi, okay? What is the value of xi? If each step here, if each patch has a distance delta x, okay? Delta x, okay? So this is the distance between each patch. So so the patch 1, actually patch 1 here, I would better call it patch 0 is at 0, patch 1 is at 1 times delta x, patch I will be at I times delta x, okay? Yeah, so this position xi is just I, the position in the distance from the patch 0 is just I times delta x, okay? Yeah? So this is the position in space of the patch I, okay? And now I'm going to say, okay, instead of writing this equation as ni, that is the population of patch I, I'm going to write this equation like this. I'm going to write this as dm dt dn dt of the population at the point xi. So here it looks like I just changed the notation, but actually I'm trying to do something more fun here. That is actually I'm going to treat n of x no longer as a set of values, but as a function of x, okay? So this, I'm going to represent this as a density of values, okay? I'm going to pretend that I didn't have discrete patches. I'm going to pretend that this is actually, n is actually a function of x, okay? Does that make sense? Yeah, okay, so let's see if we can make this work, right? And now the trick is beginning, right? So now the trick is beginning. So I want to write exactly what is up here, okay? But in a slightly different way. So I'm going, you see that I can put m in evidence, right? Yeah, I put m in evidence, okay? So this is going to be m. I think I will need a bit more space. So I'm gonna put dn dt of xi is equal to m. Now I'm going to make a trick here, okay? So I'm going to multiply this by delta x squared, okay? Why? Why? You have to wait and see, okay? Yeah. And now I have 1 over delta x here. And now I write these terms here, okay? So this is minus. So you see, I multiply by delta x twice. I divided by delta x. And now I have to divide again by delta x, okay? So there will be another delta x inside, okay? Okay, now this term here is n minus, all right, we'll write it like this. So this is minus ni, or what is ni, right? It's n at xi, okay? So ni is n at xi, right? And I will put with the minus in evidence here, minus n at I minus 1, right? So what is n I minus 1, right? So it's the previous xi minus 1 is xi minus delta x, right? The position of the previous, of the left patch here is the position of this patch minus delta x, okay? Yeah, so this is minus n of xi minus delta x, okay? And I divide this by delta x, okay? This is delta x with delta x, gives me delta x squared. That cancels with this here, okay? This is the first term. The second term is similar, right? So I put plus, plus, now I have the m is already factored out here. I have ni plus 1, ni plus 1. What is ni plus 1? Is n at the point, at the patch to the right, at the point xi plus 1, that is at xi plus delta x, yeah? Okay? So this is n at xi plus delta x, okay? Minus, oops, here, minus n at I, okay? N at the point xi. Okay, and now I also have the delta x over here. Okay, so these are my equations here, yeah? Okay, people, so this is a bit of algebra finally. So this is a funny property that you start a course with a lot of programming and computation, and then eventually it all turns into math, right? So, yeah. So far so good, yeah, not too complicated. Okay, so, but now I'm going to do a trick here that is, okay, I want to go to continuous space, yeah? Continuous space is when they are, the separation here is infinitesimal, right? Yeah, I have actually an infinite number of points here, yeah? So this means that I want to take the limit where delta x is going to 0, right? Delta x is going to 0, yeah? Okay, so what happens to these expressions here? What are those expressions? Yeah, can you recognize those? Yeah? So these are the, so this is n at xi plus a small delta x minus n at xi divided by delta x. This is exactly the definition of the derivative of m with respect to x, okay? So this is the derivative with respect to x, and this is also the derivative with respect to x. Yeah? But then there's a funny thing here, right? There's a funny thing here, because this is the derivative with respect to x, and this is also the derivative with respect to x, right? And it looks like I'm calculating them at the same point, and this has a plus, and this has a minus. So it looks like they should be 0. They should cancel out. That's funny, right? That's kind of weird, right? Not really, not really. So this is the part that's tricky, right? So this is the part I'm kind of I wave my hands around and tell you, okay, but this is calculated at the right, you see, because this is calculated from the patch to the right, so it's actually calculated here, right? So let me enlarge this thing here. So I have xi here, I have xi plus delta x here, and I have xi minus delta x here, okay? So one way to think about these derivatives is that I'm actually calculating then this point minus this point divided by this is actually the derivative. So this thing here will be the derivative of m with respect to x. But this is at the midpoint between xi and xi plus delta x, right? So this is at xi plus delta x over 2. And this thing here is nxi minus nxi minus delta x, right? Divided by delta x. So this is the derivative. So this is the derivative of m at a point that is to the left of xi, okay? Right? So this is what I actually have. I have this here minus this, okay? And I have all of this stuff here divided by delta x. So I have so you can think of the derivative of n as another function, and I'm taking it at this point here. So let me change the color. And taking it at this point here, minus it at this point here, and taking and dividing by delta x. So the distance between these 2 points is exactly delta x. When delta x goes to 0, this gives me the derivative of this function dn dx, okay? So this is the expression for the second derivative of this function, okay? Don't worry if you're confused, okay? This is a bit confusing, but doesn't matter, okay? It doesn't matter. So, so in the end, all this expression here, from this onwards, right? All of this is just an approximation, right? Or it will be exact when delta x goes to 0. This is exactly the expression for the second derivative of n with respect to x at that point xi, okay? So this whole thing here becomes gn dt, and now I will change the notation a bit because now n, right? N is no longer just a function of t, but is also a function, n is a function of both x and t, right? And when you have a function that has more than a single parameter, right? So it's depending on more than one variable. When I take the derivative, I have to be careful that when I derive with respect to one variable, I keep the other constant, and then there's a special symbol for that that is called a del, okay? Instead of a g, I write these derivatives with a del, okay? So this is a more technical thing, but yeah, so this is going to be del n dt. So del n dt at the point x t is going to be m delta x squared times all of this stuff here that became just, this was the second derivative, right? The second derivative is written like this, okay? So this is times the second derivative, but now using the del notation, the second derivative of m with respect to x, okay? Yeah? And now, what's going on here? I told you that delta x is going to 0. So this stuff here is going to 0 as well, yeah? But remember that as I increase the number of patches, okay, I have to increase m as well, right? And at which rate has m to increase as I decrease delta s? Quadratically, right? Remember that to get the same spread, multiplying the number of patches by 10, I had to increase m 100 times, yeah? Okay? So this m here, as delta s goes to 0, m is proportional to 1 over delta s, okay? So I would call this thing here, I would say that this is a constant, actually. It doesn't depend on delta x. I say that all of this here is d, right? D. So m delta s is this z, that is all the diffusivity or diffusion coefficient of this population. Yeah, and then this stuff here, so let me erase this part here. So, yeah, over here, so I'll just put a d here. Yeah, maybe let's write it like this, right? So this is, yeah, so this is too big to me, right? So let's write it again here, right? So this is finally, so this is our famous, very famous diffusion equation. Also known as heat equation, yeah? So you see, when you look at this, right, so if I just if I have started that like just throwing this equation at you, right, it would be kind of hard to understand what is behind it, right? Yeah? But then I try to build it step by step to see that this is nothing more than migration between points that are very closely spaced, and migration only happens to the nearest neighbors, okay? Yeah, so this is essentially what is behind this equation, okay? Of course, you can look at this and say, oh, it can look confusing, okay? Maybe you don't know anything about partial differential equations, so this is a partial differential equation, but it's nothing more than this stuff here. I'm taking a fixed region, I'm dividing it in many small pieces, and telling you that migration only happens among the nearest neighbors, and then what happens after a long time? The population tends to spread out and be evenly distributed over the whole space. Yeah? Is that kind of palatable for your first, well, physicists might already know about this, okay, but for people that have never heard about this before, does that make sense? Can you get a little bit of feeling about what this kind of equation does? Yeah? Okay, good. Let me see if we have, no, we have already gone over time. Let's see if I had something else planned here. I don't think so, but yeah, so here it is, right? This is diffusion equation. And now the only thing that I didn't talk about is that actually I don't have to, if I want to include growth rate, I can just sum the logistic term here, right? So at each point, besides the migration, we also have a growth rate here, right? So I can just sum R times M times 1 minus N over K to each point, right? And it means that each point, the population grows taking into account only the population at that exact point, okay? Just like we had in the patch model. So the growth rate is only with the population at that point, not the population over all of the space, okay? So if I sum, let me write this in the board because it's really important, right? So if I include another term here, this will be, if I include another term here, for instance, a logistic term, this here is called a reaction diffusion equation, okay? Reaction because this is the diffusion term, this is the reaction term, that is the growth term, but reaction because it was used first in chemistry, right? And in chemistry, species don't grow, they react, right? They say they have a, yeah? So this would be a growth term in ecology, right? Reaction diffusion equation, okay? And this is the basis for most of theory in spatial ecology, okay? Nice, people. Thank you. We will talk about this a little bit more tomorrow, I think. But then I think it was a long class already. Okay, thank you.